Hi, my name is Johanna Stewart, and this is my video report for the 6th physics lab on magnetic molasses. So the purpose of this lab was to collect observational data of a magnet that was falling through a conductive tube of aluminum foil, and then also model this magnet and tube interaction using code, and finally compare the computational predictions with the actual data. Some key assumptions are that the system is only going to undergo forces caused by the magnetic field and gravity, and as a brief preview of the results, the time it took for the magnet to fall through the tube was of 0.876 seconds, and the time estimated by the computer was 0.477 seconds. So even though most of the calculations were done through the computer, the formulas and principles that we need to keep in mind, first of all, are the field caused by a magnetic dipole, Biot-Savart's law, and Faraday's law, all of which's formulas are stated in this slide. As for the experiment, this experiment was fairly simple. We had a tube surrounded by sheets of aluminum. We calculated the length of the tube, the width of the tube, and the inner diameter of the tube, and it's all stated on the slide. We also had a magnet and made it fall through one end to the other, while the tube was held vertically, and we repeated this 5 times. So we had our system that was the bar magnet and the tube and the surroundings, which was everything that was outside. And as for the coding, we start by defining the initial conditions, such as the measurements and the constants from the tube. We also have the more measurement from the mass, and also we define a function that calculates the magnetic field that is created by the bar magnet or the dipole magnetic field. We also have defined this function that uses Faraday's law to calculate the rate of change of flux. This is what we have at the top of the image on the slide, and also we have another function that starts defining forces. First we have the gravitational force, and then we also define the magnetic force that is exerted on the magnet, and we add them both up to get the net force. And finally, we calculate the velocity and the position of the magnet, and this is all used for this this graph on the left that allows us to visualize the magnetic falling through the tube, and then on the right we can see the graph that displays the velocity versus time of the computational model. So some sources of error are that the magnetic didn't fall straight from one end to the other. It tumbled while falling, so there was some friction between the magnet and the walls that in real life may have caused the magnet to delay its time of descent. And for the what if questions, we have the first question, that is, what if the resistivity of the conductor were reduced as close as possible to 0? So if the resistivity of the conductor was reduced, then the current produced, and thus the opposing magnetic force, is going to be much stronger because the resistance would lower, and this means that the magnet would feel a much stronger magnetic force that would kind of work against gravity, and thus the magnet would fall slower. And finally, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So this means that if any holes or slots are cut into the current to the tube, then the current that is flowing through the tube would be disrupted, making the magnetic field, and thus the flux that occurs due to the magnetic field, go down, and then the force that's caused by the flux be decreased as well.